Let me first show, because what if we had an equation like this? Actually, let's make it squared. Well, see, what you would think, yeah, we kind of would, but there's something else we have to do also. We could do. We could do the product rule. Let's see. So it's going to be 2x plus 3, 2x plus 3. The derivatives are 2 and 2. So it's 2 times 2x plus 3 plus 2, 2x plus 3, which makes it 4, 2x plus 3. That's the derivative. This is y prime. A lot of work. There's a shortcut called the chain rule. The chain rule says this. First, it's a two-part process, all in the same equation. Take the derivative of the outer part, like we normally do. Bring that down and subtract 1. And leave the inside alone. So derivative of the outside, leave the inside alone. Times the derivative of the inside, which is 2. So 2 times 2 is 4, 2x plus 3. And there we have it. If I was going to put it as a rule, let's see, f of x to the power u. G of x, I'll use that. So the derivative no, we don't do derivatives, we just do, so it's n f of x n minus 1 times the f derivative. That is in nutshell, the condensed version of it. So just take the derivative of the outside first, subtract 1, times the derivative of the inside, and you're done. So let's look at our first example here. Y is equal to 3x squared plus 1 to the power 2. What's the derivative? Yeah, the derivative of 3x squared is 6x. So the answer is going to be 2 times 6 is 12x times 3x squared plus 1. You could, of course, you could distribute all those, get rid of the parentheses. 36x cubed plus 12x. And that's your derivative. which brings us to the next one. An object moves along the x-axis, so its position at any time t is greater than 0 is given by x of t equals cosine t squared plus 1. Find the velocity of the object as a function of t. So since this is the function that says it moves along that line, this is your position function. How do you find the velocity? First derivative. Because this is your position function, that's s. So we'll take the derivative of cosine t squared plus 1. So we do it both ways. We do it, the outside is cosine. What's the derivative of cosine? So it's negative sine t squared plus 1 times the derivative of the inside, 2t. So it's negative 2t sine t squared plus 1. That's your derivative, that's your velocity. This one says, instructions for this one says, differentiate with respect to x. What does that mean? Find the first derivative. So this is y equals sine x, or sine that. So the derivative would be, so the derivative of sine, because I, not negative. X squared plus e of x times x derivative is 2x, derivative of ex is ex. And there's your derivative. You're looking like it has 3 heads.
So you think they just solve that?
I just, I put everything in front of the sine cosine term. Because I don't want to get mixed up that, because you will have sometimes where this could be a big equation. It's just a simplicity form, just so you don't get confused. The same goes with e functions. Y equals e cosine x. The rule for e function, if the exponent is a function of x, then the derivative is eu du. Leave, in other words, in this case, leave it alone, e cosine x times the derivative of your exponent. What's the derivative of cosine? So it's negative sine x times e cosine x. Now, like the example in the sheet says, if y equals ex squared, the derivative would be, leave this alone, times, what's the derivative of the exponent? So that's your answer, two x e to the power x squared. What do y'all think so far? Am I going too fast or is this pretty straightforward? Didn't I tell you that this stuff's gonna get a lot easier? Now we have the tangent of 5 minus sine 2t. This one you're gonna hate. Because it's got a couple of nested stuff. So the derivative. What's the derivative of tangent? Secant squared. Yeah, we did it earlier. Example 5. It's secant squared. So it's secant squared of 5 minus sine 2t. So that's the outside. Now we gotta take a derivative of the inside times the derivative of this side. The derivative of 5, 0. We have minus. Here we have another nested one. So the derivative of sine is cosine 2t times, what's the derivative of 2t? Because it's not negative, it's the negative of sine. It's a minus problem. See, that's what I got in trouble with last time. So it becomes negative 2 cosine 2t times secant squared 5 minus sine 2t. There's your answer. Yeah, because this one here was the sine of u. The sine of u is the derivative of the outside times the derivative of the inside. We're almost done. We're almost done. Example 6. A. Find this derivative. 5x cubed minus x to the 4th to the 7th. What's my first step? Bring the 7 down. So it's 5x cubed minus x to the 4 to the power 6. Now times the derivative of the inside, which is very good. So it's 7 times 15x squared minus 4x cubed. 5x cubed minus x to the 4th to the power 6. If you wanted to, you can distribute that, but I'm happy we got that far. The derivative of 1/3x minus 2. Do it without using the quotient rule. Use the chain rule. Anybody have an idea how to do that? It has something to do with the exponent of the denominator. Because top is just one, so it really doesn't do anything for us. But this one's on the bottom. If we bring it up on top, we got that. So the derivative, bring that down and subtract 1, we get that so far. Times the derivative of the inside, which is 3. And that's our derivative. Now the derivative of sine 5x, sine to the 5th x. Which I'll get. Five sine 4x times what's the derivative of sine? No, it's not. It's positive cosine. Sine to cosine. So that's our answer. We have 5 cosine x sine 4x. E to the power radical 3x plus 1. For this one, it's easier if we use substitution. Let's say that u is equal to 3x plus 1. Because now what this thing says is, since we have e to the square root of u, we can rewrite that as saying e to the u to the 1/2 power. So the derivative is e u to the 1/2 power times the derivative of u to the 1/2 power, which is 1/2 u negative 1/2 du. I brought the power down, negative 1/2. I brought the power down. No, so positive. It was positive. I brought it down, subtracted 1, and then took the derivative of the inside. So du is 3. That's u. So it's e to this equation times 1/2 e to the power negative 1/2 u du, which is 3. E. The derivative of u is 1/2 u, not e. That's where I messed up. That's just this right here. So it's 3 times 3x plus 1, that's u, to the power negative 1/2 e to the power square root 3x plus 1. And there's the answer. Yeah, they get ugly pretty quick. Okay, now the last two questions of this section. Let's see, for example, example 7. It says we have is not differentiable at 0. However, the function is differentiable at all other numbers. This equation is differentiable everywhere else except at 0. So we have to figure out what is the formula for this. Or x squared. Square root of x squared. In other words, we take the derivative. We now have u is x squared. You can't cancel those because this has to represent the absolute value of x. So what we have here is that we have u to the power 1/2. 1/2 u to the power negative 1/2 times du. Since u is x squared, du is 2x. So we have 1/2 u, which is x squared to the power 1/2 down here, times 2x, the 2's cancel, x over square root, which makes it x over absolute value of x. So because of that, on the left side of 0, it's -1. On the right side, it's +1, which is so happens to be so are the slopes. If you think about it, the absolute value of x looks like this. The slope here is -1. The slope here is +1. Now, for example 8, it says show that this function, show that the slope of every line tangent to this curve is positive. Well, it's pretty easy because when we take the derivative of this odd exponent on the bottom is going to become 4. So that means this could never be negative. But no, we'll do that because it's, I kept you guys way, we'll do this one next time. I apologize. Thank you all. I'll tell you what, I'll give you next week and the week after that. You'd have to come to class. Thank you all very much. See you all Wednesday. I know, I can see once your eyes start getting glazed over, I said, I better shut up. Yeah, that's why I was this past weekend at a conference. And on what? When it comes to games like that, even trying to use artificial intelligence to use virtual reality, it's a novelty. It's a game. Everybody who studies